Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're going to talk about manufacturing optical fibers in space. So let's dive deep into it. So what exactly is the problem that we need to do this hula la la in space? Well, reality is our world runs on fiber 24 into 7, meaning if these things get broke, yeah, we did. Like fundamentally, and it is used on fundamental level, from gyroscopes, basically your plane navigation and all that, to your data transmission of everything, and lasers, every industrial process, and sensing. Like how the heck do you think people know what is the temperature of oil well? Fiber optic sensing. So if we cannot get quality fiber, yeah, national economy and everything, and national security, global security will be compromised. So fiber is a high priority item, so to say. Now, problem is the fibers that we use right now, the silicon oxide fiber that you can get, those puppies are very inefficient. Now, how the heck do you measure efficiency or inefficiency? Well, to stabilize that, we created a unified measurement, which is dB per kilometer. Basically, how much dB you're gonna lose. And why dB? Because again, we are talking about something logarithmic, not linear. Again, you can use linear numbers, number would be huge, so we use decibels. So you are looking at theoretical maximum of 0.14 in terms of transparency to 0.17. Now that is bad. That is bad. Like, that's useful, we make this, but that's bad. Now it is specifically bad because this cannot happen unless we have yttrium doped fiber amplifier, these puppies. Now, why do we need that topic? Here's the deal. You can, right now, you can go to a company and it's like, hey, I need a spool, like completely extruded, one spool, unbroken, of like, let's say, 10,000 kilometer long spool. They can give you. It's like, bro, take it and go. That's minor inconvenience. That's like, okay, how the heck are you going to ship the spool? That's the only issue. But we can't use it simply because of this loss. The loss is so much that if you send GG amount of fiber power, as you know, just till the point of where fiber actually starts to burn, just below that, it will lose all its power generally by the time it's reaching 70 to 80 kilometers. Most of the time, it's almost like a AC line. You can't send to a very far distance. So we use these puppy. So this yttrium doped system, basically there is a separate spool of fiber, a lot of them, coiled fiber, which has a laser diode pumping it. So okay, that laser diode pumps lasing material. Lasing material is the fiber. What happens is basically photons comes from here, which is the signal photon with the pulse. It gets turbocharged. Basically, the doping energy is so high, it's like dumps into it. Basically, it triggers trigger mechanism. So all the bits get replicated on the other side perfectly with amplification, and you have zero conversion. In the older days, like very old, like 1997 kind of old, we used to have electrical, basically photons came in, a receiver literally received a photon signal, converted into electrical, re-amplified the circuitry, cleaned up the all noise, data rate and all that, and then retransmitted with laser. That added a lot of latency. This became useful, reliable, so now we rely on solely that. And if you ever wondered how the heck sharks find these cable and chew through it, yeah, because of those puppies. They require power. How the heck are you gonna power something hundreds and thousands of kilometers? Well, you don't. So you send high voltage DC. Again, if you study electronics, you know you can't send AC long distances. Capacitive loss will destroy it, and God help you if you're trying to do undersea. 80 kilometers is the maximum. So they send high voltage DC and very high voltage. Now, to make sure the loading on the circuit is balanced, one side will send 5000 volt plus, another side will send 5000 minus, or 7000 plus, 7000 minus, and they use earth as a return path. So this, all of this is in series. Each of these blocks is in series. Each of them drops, like, give or take 50 volts, and the power supply on the both ends, basically the massive power supply, they are generally working in such a way to have constant current. They are designed in such a way that they should always push or pull, based on the other side, 1 to 2 amps. Amp wise is very low, but again, you have DC system, you have a cable, you have a current going through it, it creates the magnetic field. Now, it's not AC, it's not super easy to find, but sharp can still find it, and sensitive electronic equipment are like, bro, it just goes bro. So yeah, that's why these are not very easy to hide. And because you have to splice the giant cable, weld this puppy on, then drop it, yeah, it's expensive. You would think the fiber is expensive. Fiber is free comparatively. The moment you start to add a price of this and all the hassle that we need to do to make this thing work, yeah, ain't cheap. Flat out ain't cheap. So this is a fundamental problem. Like our world is running on it, but we have already, as of 2026, because of AI, reached a point where this is becoming a bottleneck, because again, they do break, they do malfunction. Right now, there are scenarios where fiber rerouting has to be done because repairing the fiber could take as long as like 40 days to 50 days. So world is like almost reaching a saturation. It's like, bro, we need to do something better. You can't do better because physics is limiting you to 0.14 decibel per kilometer. You can't do better than that. So we have reached the saturation of this technology. And again, there are certain limitations and laser also, but let's dive deep into that. So ZBLAN. Now ZBLAN is basically, we have reached upper limit of silica glass. So somebody is like, okay, what's the window of it? Window starts from 850 nanometers, goes as far as like 850 is transparent, peak transparency, and then dull, and opaqueness. So it's a V notch. So peak transparency is 1550. Now you can easily find this. Look into any router, optical router, any router. Generally the numbers will be always in this domain. Even though fiber can handle here to here, the problem is the sweet spot. The peak transparency is in this, the V notch. Now that notch is very tight. That gives you 35 nanometer of wiggle room. So if you can cram as many laser beams into it without causing interference, you can keep cramming it, give or take. Like I think highest somebody has tried is 128. 64 is like super easy, because be mindful, that means every laser, it's literally like half nanometer apart from each other. So again, some people are trying some new technique, but there is a physical limit. The highway thickness is only 35 nanometer. Compare that to heavy metal fluoride glass, ZBLAN. This puppy can give you a broader window. So its window starts transparency as 400. It's almost super continuum laser, 400, and then it drops to peak transparency 2500 nanometer is like mid infrared, and then it still has some transparency as 4500 nanometers. So the window is much wider. It's like, whoa, it's wide. And the V notch here is much blander. So you can achieve that 0.01 decibel per kilometer at 300 nanometers, as in like you have so many lids. Mathematically speaking, whatever your channel count is in a normal fiber, multiply that by 3, you can easily do. Now this number is the sweet spot, 0.01 decibel. Because it's decibel, you might think, oh, it's a 10x better. No, it's decibel. It's exponentially better. That puppy means if you can make a spool long enough, like one unbroken fiber, it will go from one coast to another coast without any issue. Heck, you can go from Antarctica to Atlantic without any issue. It can cross sea without a single goddamn repeater. You do not need repeater, not less repeater. You don't need repeater. That's how big and significant it would be. This is the theoretical upper limit of optical communication. So this magic crystal. And there is other advantage also. If you can make zebra crystal, like we can make it, but small. We can't make it giant puppies. If you can make this also is amazing lasing material for a specific wavelength of mid IR. Right now we have daddy lasers, which are like super strong. We cut metals through lasers like, bruh, don't even think about it. But the moment you have to deal with human skin, it's like, nah. If you use that laser, it will just punch through it. So how the heck optometrists use laser? These lasers are generally in 2940 nanometers. They are in a very specific mid-infrared. Benefit, water loves that wavelength, so it explodes. So they fire the laser, water goes kaboom, tada, fresh skin. So that's how they can deal with skin, almost like layer by layer. They're like, okay, layer 1 removed. They're firing lasers on it, but only layer 1 will, because water will instantly go kaboom. And it is so amazing that people have tried inside human body to stitch things using this laser. It does work. The problem is we don't have a fiber to route it. So this hard pipe that you are seeing, they are actually hollow rod with mirrors. That's one design. Another design is a hollow pipe, because thankfully the wavelength is long enough. You can have a pipe that has coating inside, so it's acting as a hollow waveguide. That is also allowing you to do that. But again, what we want is a laser surgery done on the same scale as, keyhole surgery. So if you can have a like this can be as big as it needs to be, that does not matter. But the end should be very small. You should be able to have flexibility. Fiber can give you that flexibility. So medical people are like, bro, shut up, take money, give me that right now. And they do not need large one. They do not need like 2-3 meters. They're like, bro, done, go home. For example, carbon fiber. If you want to slice carbon fiber, this wavelength is perfect. You could try ultraviolet, but it is idiotically inefficient. And you can try mid-infrared. It will cut through it. It's just not great. So fundamentally, if you're dealing with polymers, if you're dealing with carbon fiber and missile blinding lasers, they love this material. Problem is we cannot grow large enough of it, and God help you, we cannot grow fiber of it, like flat out. We know how to make the fiber, duh. I have made a video about it, manufacturing of fiber optic. I am assuming you have seen it. We know how to deal with that. It's just that the moment we take this and try to make fibers out of it, crystallization and gravity fires missiles at us. So we can't make it. Perfect material is there. We have known this from 1990s. We just can't make it. So why gravity is our enemy in this? Well, it's a super alloy class. It's not like one compound. No, it's super alloy. So it has zirconium, beryllium, lanthanum, aluminum, sodium, God knows what else. So this is a fundamental issue. What does that mean? That simply means when you're cooking this puppy, you have buoyancy, as in heat source, it starts to have convection. And because you have so much material, the behavior of the soup is not uniform, and convection current triggers crystal formulation. And you want amorphous, you want just like honey, not crystal. Honey, crystal. You don't want crystal. And you have convection, crystal will happen. You have cooling. Basically, whenever you cook something, you let it cool down, right? Ingot, you need to cool it down. Here's the problem with that. The moment you cool it down in Earth, it will start to do what we call gravitational settling. And again, especially it's hot, it can vibrate, and it does vibrate. The heavier elements on these channel, they start to go on the lower end, and the upper one separates based on gravity. So that creates the issue, what we call density separation. Not good. Then you have cooling. Like we have to rapidly quench it. That's the reason why we can only make small crystals. We cannot make giant 3-meter crystals that we use. Preforms for fibers can easily reach 3 meters long. We can't do that with this. Like Earth's gravity will not allow it. Like only this like marker size we can do. Cooling, because again, if you try to cool it very fast, the surface area and the convection currents start to happen, and then that leads to crystal formulation. Basically, we can't get honey, we end up with crystals. No matter what we do, we end up with crystal. This happens if you do it in 1G. This happens if you do it in micro G. Now be mindful, we have done this as early as 90s using that vomit comet plane. And yes, it did work. That's how we know. Not only theoretically, we know that this happens. People pulled fiber strands, and it's like, oh, in 0G, you can pull precise. Oh, thankfully, it does not require very high temperature for pulling. Normal fiber requires like 2000 to 2500 degrees Celsius for pulling. This puppy is like 300. Basically, my 3D printer can do that. So, fundamentally, crystal growth is your enemy, because if you have this sort of crystal growth, the moment you fire laser through it, those crystal will absorb the light, heat up, and refract it, and that will self-destruct if it's high power enough. And if it's not high power enough, it will have so high attenuation that signal will not go from one end to another. And 0G is the necessity. Without that, you're not gonna get that clean fiber. You're gonna get this noisy fiber, which is, we still make it, we still use it. It's not that great. Like if you really want to send like even few watts of power of that laser, you have to like have multiple bundles of it. So each one does not burn up. And even then it's like, eh. So gravity is the enemy in this. We want smooth. So demo, again, this was done in 1990. So it's uniquely suited to actually do it. Be mindful, people were trying to do this in shuttle era. So the idea was you're gonna have preform. Now again, we can't make a huge ass preform, but however we can make, theoretically it said that you should be able to pull as long as like 10 to 20 kilometers, maybe 30, based on gravity and calculation, like preform can be that size. Again, it sounds 30 kilometers sounds huge, but it's like it will be this much. So you have a preform, you have the heater, and then you have a puller. Now here's the deal. You should not touch the fiber, but again, the puller will be the sacrificial part. Once you pull it through, you send it through the coating part. Without coating, you should not touch it. So you coat it with a UV resin, and then you UV cure it, then it goes to the final spool, take-up spool as they call it. Now all this can be done simply because the pulling force is very low and your pulling speed is tiny. Compared to Earth puppies, which has like, giant racks, which are like 100-foot tall, like draught towers we call them. Yeah, those puppies are running at bonker speed, like 100 meters per second. We need to use helium convection to cool those puppies. This is 300 degrees Celsius, running at 1 centimeter per second. So it's easy. We can easily radiate the power away. It cools down, don't even have a dedicated cooling stage, and you just coat it, harden it, wrap it up. So it does work. We have tested it in the 90s, and Because of the slow speed, the whole machine can be this size. And these are actually in ISS right now working. I'm not talking about something could be, would be. Done. That stage has been done. This is from Thorlabs. This, if I'm not mistaken, Flawless Photonics. They are there. So, okay. We have the preform, we had the theoretical idea. Have we ever actually pulled any fiber? Yes, the world record right now is more than 700, but 700 is like you can just order it if you want. Again, they will not sell you because they are still in early stage, but it's been done. Like 700 meters is like they're counting it. 1 kilometer, as again, there are some snag happens, this happens, that happens. People are working on it. 1 kilometer, you can like, I can pretty sure by 2028, 1 kilometer long unbroken strand would be like, bruh, who cares? So that is there. Now, why do we need very long strand? If the fiber is so lossless, why do we need it? Well, because if you have lossless fiber and lossless fiber, you do this to them, basically splice them, splice at 0.01 decibel loss. So that loss piles up. So if you have very strong, short strand and you want to make transatlantic fiber, yeah, because of the splice loss, you will be like, yeah, the signal is losing. So to have that, ideally you will have one, but mathematically you must have 20 kilometers or 10, bare minimum 10. But again, people are saying that 10, it's so messy that it's like barely useful. 15, you have wiggle room. 20, shut up, take money. At 20, it's like, shut up, take money. At that point, it's like, bro, we have nothing. We just have fiber. The fiber price, even though it's millions of dollars because it's coming from space, it still would be free. In contrast, because you will not have high voltage lines, you will not require 10,000 layers of armor shielding because most of them are for the power system, and you won't have repeaters every few 70 to 80 kilometers. You won't have shark biting it. And again, if some saboteur wants to find it, it's much harder to detect optical fiber than it is to detect something that is carrying 1 kilowatt of power and has like 20,000 volts. So fundamentally, and even if you are only able to make 700 right now, medical industry, missile booming industry, laser industry is like, when can I buy that? Like when? Like I do not need to know about the price. When? So demo has been done. Done. Take it and go home. I could not find the design of this because this was NASA published. This is not published. If you know where this is published, do tell me. So what can we expect in the future? Well, here's the deal. This is a start of profitable space manufacturing. It's fun and dandy to say, oh, we're going to make money. How? Like you might be like, okay, what about tourism? Yes, it can work, but it has very ebony flow. Sometimes it's like YOLO, and sometimes everybody's broke. And I'm pretty sure anybody who studies economics knows like more and more people are becoming broke than they are becoming rich. So few people, they will be bored. Like Jeff Bezos, how many times he will go to space? Like few times he will do, but then he'll be bored. So this is the issue. You need to, like, if you want to build these things, you need to justify the economics. Thankfully, fiber is high priority enough. So theory, done. Lab scale, done. Prototype run, done. Where we are, final validation. As in the spool is on Earth, going through final validation. And I'm pretty sure they have sold their spool to defense contractor and medical laser people. They're not going to sell it. They are just going to like validate it. Does it work how we expect it to work? Can we pump hundreds of watts of laser power and it does not burn? Can we send kilowatts of laser missile blinder through it without it going kaboom? That will happening right now. And again, that's the only way where you can justify something like this, like, you know, Axiom space station, vast space station, orbital reef. Okay, you have something where a lot of people are going and coming out. Cool, awesome. To do what? Well, to make fiber. And the target right now, mathematically, example is 10 to 30 kilometer preform. That's maximum you can do as of now. Eventually, the final aim would be like, let's assume this works and it's a really good, stable, fine and dandy. Eventually, somebody figure out how to make the preform there also, meaning the furnace part. If they can do that, that would be magnificent. That would be like, damn. That would be damn. But again, that reaches with high temperature territory, so it's difficult. But again, there are other people also trying some other things, which again, let's hope it works. For example, there was some company trying HIV medication, which I'm like, okay, is it high value enough? Because again, there is a paradox. It is high value if you can make large enough of it. You can't make large enough of it in space. Fiber is high value enough. Again, let's say once they are proven and once the laser starts to hit the market, even few meters of unbroken strand would be like, shut up, take money today. And if you have seen that SpaceX building that disk puck that is gonna return thing, what the hell is gonna return? This. So every company who's working on this, they know, because be mindful, we have been trying this from space shuttle. We know that this works. We want it to work. Need has gone bonkers because of a Russia-Ukraine war. Second, because of basically AI boom. Everybody's like, shut up, make the fiber. Even in data center, it's like, hey, wait a minute, you are telling me that instead of having 3 fibers strand, I can only have 1 fiber strand. Shut up, take money. Again, they do not need very long one. They just need to connect the data center with each other. They're like, bro, me good today, we good. So future is hopeful, financially speaking. So this was my presentation on what the hell you're gonna do in space, how the heck you're gonna make money. Hopefully you have liked it, learned from it. In that case, please click like the button. If you have enjoyed it, click the hype button. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.